Okay, let's talk about these algorithms. Oops, algorithms for, and we're going to start with forward elimination. And I want to introduce one other concept before we do this. We've been working with a x. This is a 1, 1. Let's say it was only a 2 by 2. I knew we would never solve that, but 1, 2, and we'd have two things here. And we have an x vector equals b. Okay, so this is ax equals b. Now, what people usually do is, or commonly do, is we know we're going to have to do a lot of row operations on this matrix, and we need to do them also to the b vector. So typically they put them, or commonly, they put them, they put the b vector in with the A matrix and call it the augmented A matrix. So the new augmented A matrix looks like this. It's got A things in it, and then it has the B things in it, right? So this would be A, this would be B. All right, and so that way you can operate on just a single matrix without having to separate out this B vector. It's more intuitive if you can call these things in your algorithm B1, B2, B3, but this lets you take advantage of some efficiencies. You just get to write your code a little more concisely. All right, so the way this looks is you go, and I'm going to write this generically, so it's not in a specific language. So I'm going to say for k equals 1, 2, and minus 1. All right, and you know in MATLAB there would be a colon here instead of 2, but it would be different in Python, it would be different in Fortran, it would be different in C. So I'm just writing this generically for us, so you know this is a for loop. And this is how many elimination steps. Okay, so because you know you don't have to eliminate the first row, right? So, but you need to eliminate all the other rows. So that you want to do n minus 1 rows. All right, so how many elimination steps is this first one? All right, and then we know that for any elimination step, what we need to do is eliminate all the stuff in the columns below that whichever pivot we're looking at. And we call these guys pivots here on the diagonal. Okay, so you have to eliminate everything below that diagonal. So we want to go down that column. So the way we're going to do that is for I equals k plus 1. So if you think of the first elimination step as we want to keep the first row and we want to start operating on the second row, that's why we're at k plus 1. All right, to n. All right, we got to get down to the bottom of the matrix. All right, and for that step, we need to calculate that ratio. You know, we need to subtract the ratio of something from here to make this be 0, right? So our ratio is going to be a sub ik equals a sub ik divided by a sub kk. All right, so this is our elimination step. This says the diagonal on our elimination, we're working on, we want to divide by that. And what are we dividing by? It's this guy, right? We need to find that ratio so we can subtract. Now, so this is the ratio, and this is just a place to put it, all right? We don't actually need to know what this is in the future because we know it's 0. But we need a place to write this ratio. So this is one of those sneaking computer science tricks where instead of inventing a whole new vector or a new variable and needing to store it someplace, we're already operating on this matrix, and we have a big chunk of the matrix that we aren't going to need. So let's put some other stuff in it. We're just using it as scratch paper, basically. Okay. So down the columns. Let's add that here. Go down the columns. This is our ratio, and we're storing it on scratch paper. All right, and then we need to, if we're going to perform row operations on this part, we have to fix the rest of the row too. All right, so this next loop is going to be fixing the rest of the row. So this is going to be for j equals k plus 1 to n plus 1. And this n plus 1 is because, remember, we've added the b vector on here, so we need to actually get beyond our n by n matrix and do this column too. So we want to fix it also. So we're going to say a sub ij equals whatever was in a minus, remember our ratio and how this all works out, all right? So we want to multiply our ratio by a sub kj. That's what we're subtracting from everything so that we get 0 here, and then we have to subtract it from everything else going that way. All right, so minus a sub ik, this is our ratio, times a sub kj, all right? And that's just where we are in the row. Or sorry, this is the stuff we're subtracting from this whole row. This is what was in this spot in the row, and we're subtracting the stuff. Okay, and so we're going to end, oh, sorry, that occurred in our code. We're going to end for, and remember that took care of our B also. So this loop is just fix the rest of the row. And then it's time to go, you've finished this row, now you need to get to the next one. And zero out the next spot below whichever elimination step you're on. Okay, and once you get all of your elimination steps done, you are done. Okay, so that's forward elimination. All right, now we have to manage some backward elimination. All right, and the first thing you want to do is, first thing is we're going to be solving for x at this point. And the first thing you do is remember that we have the b's stored off the end of these a's. All right, so let's do backward substitution. Move this up so we can see what we're doing. Now remember, we had these equations for back substitution. We wanted to do this one, that's our last one where we know such and such equals so and so, right? And then for the rest of them, we have to substitute in the stuff we know and then solve for this one. And then we have to then we have more stuff to substitute in the next time. So you know we're going to have another loop where we're going through all these terms and subtracting them from this side and then dividing by the coefficient that's here to get what x actually equals. And another thing, you remember here we were working with u and y, all right? In computers, you don't want to make a whole new matrix U and a whole new vector Y. Really what you do is, as you did your forward elimination, you notice we just wrote them back in the A and B matrices, right? Or A matrix and the B vector. We just stored, and we really stored them all in that augmented A matrix. So this gets into linear algebra and coding, and things like that we aren't going to get much deeper in this class. But I'm explaining why this back substitution algorithm is written back with X's and A's instead of, and things instead of A's and Y's and U's. Okay, so what we're going to do is we say for I equals n to 1. All right, now you're already saying, hey, wait, we can just solve directly for row n. We already know that one, but let me show you why we're doing the whole thing in one loop. All right, because we could just pop that out now. We could solve for x sub n right now. We know the answer. All right, but we're going to have it in this loop because it's kind of cool and efficient. Here we go. Because our next thing is we need to calculate that summation so we can subtract it off from the other stuff, right? So here's our summation for j equals I plus 1 to n. All right, and this is exactly what we thought it was going to be. J equals I plus 1 to n. All right. And so we say x sub I equals x sub I minus a sub ij times x sub j. All right, and 4. Now, what this does is, and then we have to do this last step. So we did this whole summation thing, and then finally we say, well, x sub I, we still have to divide by our ratio, right? Or it's by the diagonal, sorry, not by that ratio, by the diagonal. X sub I divided by a sub I. So there's the value on the diagonal. All right, so we better have a picture of this. We have a matrix that has been diagonalized. So we have all this stuff on the diagonal, and then we have these other guys. And so these are the a sub i's, this diagonal going down here. We multiply them by the x vector equals, and we're going to have a b vector. All right. But remember, we stored the B in sort of the end of the A matrix. So when we reach it, some of these guys are actually B's, is what's going on. Some of these A sub ij's. All right. So, and when we get to the end is by dividing by this thing, because we've already subtracted off all this other stuff. All right. So you start with x being nothing, and then you have to subtract off all these guys and that guy, right? And finally, you divide by the diagonal and you find out what x is. So that's what that is. Okay. Oh, and I should actually, let's just make a note. Note, x sub I is stored in a sub I n plus 1. So basically, this x guy comes in being your b vector, and the b vector has already been all modified because it's been part of here. All right, and then when you do your math down here, you wind up just overriding that old b vector with your new x vector. So it's actually like right in here, okay? And you're kind of going through the loops. Now, let me just return quickly to this thing of, if for our very first row, we don't want to do all this summation because there's only one term, right? We just want to go directly to this. And when we start, this is b equals, or sorry, x equals, and it starts out being just b, whatever our b was after we finished modifying it, divided by a sub I equals this thing, right? So for this first row, that's all we want to do. We don't want to do this summation. What's cool about this is in this summation, this loop starts at I plus 1. Well, on the first row, I is already n. So this is go from n plus 1 to n. These things don't do that unless you tell them to take negative steps. And if you don't do that, it's like, oh, this is already too big. I don't have to do this loop. All right, so it goes directly to here. And then it comes around for n minus 1. This one you say, step -1. All right, so step down. All right, so now this is n minus 1. When I get here, this is n to n, right? n minus 1 plus 1 is n. So this time it says, oh, I'm inside the bounds. I'm going to do this one time, right? Because the next time through it would be like, oh, it's too big. So it does it one time, all right? And then calculates the result after it's done its summation. All right, on the next one, this is n minus 2. So now it's going to do this 2 times from n minus 1 to n. See, so that's how this loop works, and that's how we can write this way without having a separate row for, a separate line for, hey, let's do this last row first. All right, it actually does get done perfectly fine. It doesn't add any extra terms in here because it just skips it on that first row. All right, so that is how you would convert these summations and solutions to actual code.